All right, here are reminders, some important points. Uh, First of all, Kirchhoff's loop law, which is kind of easier to say than it is to write. If you go through any uh, loop path in a circuit, that is, start anywhere and then come back to where you started, the total sum of all the potential differences has to add up to zero. So let's say I start here, and the first potential difference is the potential difference between the low and high end of this battery, potential difference A, and then there are a whole bunch of other circuit elements, B through N, right? N circuit elements in the path in total, and you add up all of their potential differences has to come out to zero, which makes sense when you realize that you are, after all, coming back to the same place where you started. The other, the other so-called Kirchhoff law is so-called junction law. Junction is where two or more currents come together, or where two or more currents leave. And the basic idea is that the total current going in is equal to the total current coming out, which is basically the same idea as the conservation of current principle. That at any point, like this point here, you have to have the same current as you have at the same total current as you have at any other point. The current coming into the junction must be the same as the current at that other point a little farther on down the line. The exit of the junction must have the same current. And again, that's one of those things that's easier to say than it is to write. Total current coming into a junction equals total current going out of the junction. Then, of course, we have the basic relationship between current and the potential difference that really makes the current flow through that much resistance. And then the ideal wire approximation, when we have just plain wire instead of a circuit element, like a battery or a resistor, there is no potential difference between any 2 points in that wire. Every point in the wire is at the same potential. Or pick any 2 points in that wire, the potential difference between those 2 points is zero. Right? Any potential difference of zero for any 2 points connected by wire alone. No circuit elements in between. And then two pieces of terminology that are good to remember. Series, a bunch of circuit elements in series means they're all in a row in the same path, and that means they share the same current because of the conservation of current principle. And then parallel circuit elements means they all share the same potential difference. And let's look at just a few examples here. So let's say we have a circuit like this, and then just imagine for some reason you've put a bunch of lamps together in a weird looking circuit that looks like this. This is just, think of this as a wall socket, a source of potential difference, and then you've got some lamp. There's one lamp. We'll just let the circle represent the light bulb in the lamp. That's the part of the lamp that has most of the resistance, and therefore having resistance, potential energy will be reduced as current passes through there, and then that loss of potential energy is a gain for the total energy in the light bulb. And as it gains energy, it glows and then radiates away that energy partly as heat, partly as light. And to keep it simple, we'll say all these lamps and light bulbs are identical. Most significant part of identical means they all have the same resistance. So, like that. And there are really three different currents here. There's the current pushed away from the battery, and then the current that is pushed away from the potential difference and into all the resisting elements. Call that just plain I. And then here's a junction where the incoming current I splits up into two different currents. We'll call them I1 and I2. So total current coming into that junction, I has to equal total current going out. And let's say we want to rank these light bulbs by brightness. Well, brightness basically just means how much energy it's radiating. You can measure that, the amount of energy radiated. Think back to waves. You can measure it with either intensity or power. We've been thinking about power recently, so let's think about power again. All of these have the same resistance. So a power equation that has resistance in it will be easier to work with because we'll know for sure that one factor is constant. So if we say that, use this one, power is current squared times resistance. And this is the same for every one of these light bulbs, then that means that power is really proportional to the square of the current. Whichever ones have more current will then be brighter, even though they all have the same resistance. So, ranking by power is the same as ranking by current. Well, clearly this one has the most current because it gets current I passing through it, and I is the sum of the other two currents, so these both have to be smaller than I. We'll call this light bulb A, B, C, and light bulb D. So light bulb A is the brightest because it has the most current. And then these two things, I splits up into two paths. And we know that I1 is not going to be the same as I2 because the path for I2 has two light bulbs, in other words, two lumps of resistance, whereas this has one light bulb, just one lump of resistance. Lumps of resistance in series, the grand total equivalent resistance in that series string is just the sum. So there's two units of resistance in this path, just one unit of resistance in this path, and if two paths share the same potential difference, and they do in this case, then if they share the same potential difference, then smaller resistance corresponds to bigger current, which means B gets more current than either C or D, so B shines brighter. And C and D are in series. Series means they get the same current. Same current means same power, so the brightness of C and D is equal. Now, one more word about what I just said. I said this path and this path are in parallel. That is, the potential difference right here, where you start the current 1 path, is the same as the potential difference right here, where you start the current 2 path. It's the same potential because they're connected by nothing but wire. And then again, this point here where you end the current 1 path is at the same potential as this point here where you end the current 2 path. They're at the same potential, so because they are connected by nothing but wire. We're just using the ideal wire approximation again. So, but the potential difference between here and here is just the same as the potential difference between here and here. So this lump of resistance and these 2 lumps of resistance taken together are in parallel with each other, because the points where current enters all the resistance are at the same potential, and the points are both at the same potential, and the points where the currents exit all the resistance, those points are at equal potentials also, so the potential differences between entrance and exit are the same for both paths. Let's look at that a little bit more systematically. So some kind of a circuit, and just keep it simple, 2 lumps of resistance, and we'll say that R1 is bigger than R2. And so again, here's a junction where current splits up into 2 paths, and we'll say that the current 1 goes this way, and current 2 goes that way. Well, they're in parallel, so they're at the same potential. Potential difference between here and here is the same as the potential difference between here and here. That is, potential difference between the entrance and the exit of this resistance is the same potential differences between the entrance and exit for this resistance. But we know from this rule how we can write a potential difference in terms of other things. Potential difference is just I times R according to this. So potential difference for resistor 1 is just the current passing through number 1 times its resistance, and that's equal to the potential difference for 2, which is just its current times its resistance. Okay, now imagine dividing both sides by I1. That gets I1, takes I1 out of the left-hand side and puts it in the denominator of the right-hand side. And then imagine dividing both sides by R2. That cancels out the R2 here and puts R2 in the denominator on the left side. So what we are left with is just R1 over R2 on the left-hand side, and then I2 over I1 on the right-hand side. And in this case, R1 was bigger than R2, so this fraction here has to be greater than 1, which means this ratio here has to be greater than 1, which means I2 is bigger than I1. And that's exactly the result that we should have expected. That's the result that makes sense. The smaller resistance gets the bigger current. The bigger resistance has less current passing through it, because that's really what resistance measures, how the difficulty in getting current to pass through. Okay. Let's take a look at this. Imagine a 10-volt source of potential difference, and it's attached to a simple circuit that looks like the ones we've seen before. Here's 3 lumps of resistance. One here that gets the total current pushed away by the potential difference, and then 2 others in parallel. And we'll say the resistance there is, let's see, 10 to the minus, excuse me, say it's 10 to the 3 ohms, 10 kilo ohms. And we'll say that the resistance here is just the same, 1,000 ohms, 10 to the 3 ohms, 1 kilo ohm. And this one, twice as large, 2 times 10 to the 3, 2,000 ohms, 2 kilo ohms. Remember, we can think of those 3 resistors as equivalent to just one resistor. One resistor of just the right value will have the same effect as these 3. That is, we can imagine a circuit where the same potential difference pushes the same current through just that one resistor, which has the same effect as these 3. Same effect really means producing the same current. Okay, now, what is that equivalent resistance? Well, first of all, remember what I did last time. I look for resistors that are either in parallel with each other or series with each other and find the equivalent resistance of just those, just only those. Well, here's 2 that are in parallel, so I can replace those 2 with one equivalent resistance that has the same effect as these 2 parallel paths. That is, this circuit here is really, I can say it's the same as 10-volt potential difference pushing the current I through that one, and then one equivalent resistance that has the same effect as those 2 in parallel. The rule for equivalent resistance of resistors in parallel is that the inverse of the equivalent resistance is the sum of the inverses of the original resistances. So 1 over that resistance, 10 to the 3, plus 1 over that resistance, 2 times 10 to the 3. And again, you're adding fractions, so you must have a common denominator before you can add fractions. The smallest common denominator is 2 times 10 to the 3, and we get that by multiplying numerator and denominator of this by 2. So what do we get? We get 2 of these 1 over 2 times 10 to the 3s plus another 1 over 2 times 10 to the 3. So we've got 3 over 2 times 10 to the 3 ohms. Remember, that's the inverse of the equivalent resistance. And obviously, it's the inverse because you've got the unit label for resistance here in the denominator. So the equivalent resistance itself is just the inverse of this. Just flip all this over. And so our equivalent is this flipped over, 2 over 3 times 10 to the 3 ohms. Notice one important point here. Those two original resistors in parallel were 10 to the 3 and 2 times 10 to the 3. The equivalent resistance is smaller than either of them. That's the way it always works. The equivalent resistance is smaller than even the smallest of those resistances in parallel, because when you've got a bunch of different resistances in parallel, you've got a bunch of different paths. And the more paths you have for current to flow, the more current that flows. And more current flowing means there must be less resistance. You don't get more current unless there is less resistance. So anyway, now for the final step to find the equivalent resistance for that whole circuit, here's 2 in series. So one resistor that has the same effect as these 2 will just have a resistance equal to this sum. So that 1 times 10 to the 3 plus 2/3 times 10 to the 3 will give us 1 2/3 or 5/3 times 10 to the 3. So 10 volts pushes the same current through one equivalent resistance, which is equal to 5/3 times 10 to the 3 ohms. And with that, we can now figure out what the what that current actually is. What I is the current pushed away from the battery, and the current that eventually gets split up into those 2 parallel paths. Just apply the basic rule to that. Current is just the potential difference divided by so 10 volts over 5/3 times 10 to the 3rd ohms, and that will give us 6. This gives us 6 times 10 to the minus 3, because we have a 10 to the 3 in the denominator. Six times 10 to the minus 3, well, it's volts over ohms. Volts over ohms always means amps. Or 6 times 10 to the minus 3 amps, or we usually say 6 milliamps. So then what have we got here? 10 volts. And then the current going this way, I, through 10 to the 3 ohm resistor, and then it gets split up. So 6 times 10 to the 3 goes through here, and then it gets split up. And we know how it gets split up. Look at that ratio again. Call this current 1, and the current that goes through the stronger resistance, call it current 2, where our rule was, say, R1 over R2 equals I2 over I1. Well, R2 is 2 times 10 to the 3. R1 is 1 times 10 to the 3. This is twice as big as this, so this fraction is really just 1/2. So I2 over I1 is 1/2, which means I1 is twice as big as I2. And that should make sense. I1, the current this way, is twice as big as this one because this resistance is twice as big. You get only half as much resistance here as here, so this ought to have twice as much current. It's 6 milliamps that are being split up at this junction, and it's being split up in a 2-to-1 ratio. So that immediately tells you what the currents have to be. Currents are like that, and this is 6 milliamps. So I1, the one that's twice as large as I2, has to be 4, and that has to be 2 milliamps. Because we figured out here that current 1 had to be twice as large as current 2, because it had only half as much resistance. 4 milliamps, and then 2 milliamps. And then if we like, we can do the last step and see what exactly the potential difference is between the two ends of each resistance. These two are in parallel, so of course they'll have the same potential difference, and this one will have a different potential difference. We can figure out the potential difference of this one just by using the basic rule. We'll call this resistor A. So the potential difference for resistor A is just current times resistance, I times R. The current passing through A is 6 times 10 to the minus 3 amps, and then the resistance was 10 to the plus 3 ohms. Well, 10 to the minus 3 times 10 to the plus 3 is just 1. So what we've got here is 1 times 6, or 6 volts. 6 volts of potential difference between here, and that immediately tells us what the potential difference is between here and here. We don't even have to do an I times R calculation again, because think of Kirchhoff's loop law. If you take a loop like this, go around here, say start here and then go around in a loop, you have 3 potential changes. Let's just look at those. First one is an increase of 10 volts. This point here is 10 volts higher than has a potential 10 volts higher than this point. So a potential change is an increase of 10 volts as you go from the starting point to here. And now as you go from here to here, you're moving through this resistance in the same direction as the current. If the current is moving this way, it's moving this way because there's an electric force pushing it this way. It has to be an electric force this way to keep it from being stopped by the drag force that's pushing backwards. So if there's an electrical force pushing this way, there must be an electrical field pointing this way, because we're thinking of this as the conventional current, which is made up of positive charges, and electric field points the same way as the force on positive charges. So if there's electric field pointing this way, electric field always points from higher to lower potential. So the moral of the story is, if you move through a resistor in the same direction as the conventional current, you are always moving from higher to lower potential. Your potential change is always a decrease. There's 6 volts of potential difference between here and here, so there's 6 volts of potential change. And then, say you're going through this path here, and you have the last potential change you'll get is the potential change between here and here. Again, you're moving in the same direction as a conventional current, so that's a potential decrease through the and we'll call that resistor B and this resistor C. And then after you've gone through that potential drop, when you move in the same direction as the conventional current through this resistor, you come out here, and then there are no more potential changes until you get back to your starting point. You have just plain wire, which is all at the same potential. So that's the grand total potential difference in a loop that starts and ends here. So the sum of all the potential changes has to be 0, which means this has to be 4 volts. And since resistor B and resistor C are in parallel, the potential change across resistor C is also 4 volts. And one last thing, just this is just another somewhat trickier application of the ideal wire rule. Let's say here's a potential difference, and then we've got a resistor here, but it's an open circuit. There's a gap. No current can flow here. So obviously, if no current can flow here, there is no current anywhere in the circuit. That's really another application of the conservation of current principle. Right? If the current is 0 here, then it has to be 0 everywhere else. So let's look at that same circuit from several different points of view. Let's look at 2 points, X and Y, and we'll say X and Y are here and here for situation A, and for situation B we'll say X and Y are here and here, and then for situation C we'll say that X is here and Y is here. And then for the last situation, X is here and Y is there. Now, if we were to rank those four situations rank them from greatest to least in terms of the potential difference between point X and point Y. Like that. Well, remember, there's no current here. Well, here, X is connected by nothing but wire to the high potential side of the battery, and here Y is connected by nothing but wire to the low potential side of the battery. So this point has the same potential as the high potential pole of the battery, and this point here has the same potential as the low potential pole of the battery. So in situation A, the potential difference between X and Y is just the battery potential difference. And then in situation B, potential difference between here and here. Now remember, there's no current. So the potential difference between here and here is no difference. Potential difference between the two ends of that resistor is current times resistance. But there is no current, so there is no potential difference. So the potential here is, of course, the same as the potential here because they're connected by nothing but wire, but now potential difference here and here are the same because there is no current passing through. I equals 0. So the potential is the same here as it is here, as it is here, as it is here at point X. So again, just like in situation 1, point X has the same potential as the high potential side of the battery. And point Y, even though it's at a different point than it was here, point Y is still connected to the low potential pole by nothing but wire, so it's still at the same potential as the low potential pole of the battery. So that means the potential difference between here and here is still the same as the battery potential difference. This is at the same potential as the high pole on the battery. This is at the same potential as the low pole on the battery. And then in C, it's exactly the same. These 2 points are connected by nothing but wire, so they're at the same potential. This point Y has the same potential as the low potential pole of the battery. These 2 points are connected by nothing but wire, so this point is at the same potential as the high potential side of the battery. So that potential difference between X and Y, again, is same as the battery potential. And then D, D is going to come out exactly the same. Well, no, actually, D is the one that's going to be different, because remember, there's no current here, so there's no potential difference between these 2 points. So in this case, for D, the potential difference between point X and point Y is 0. Potential difference is current times resistance, which is 0 current times resistance. That's the potential difference between X and Y in case D. So then the ranking was just potential difference in situation A equal to what it is in B and what it is in C, and that's greater than what it is in case D. In this case, the potential difference between X and Y is 0, and in these cases, the potential difference is exactly the same as the potential difference between the two poles of the battery. In all three cases, A, B, and C, point Y is connected directly by nothing but wire to the low potential side of the battery. So being connected by nothing but wire, think about the ideal wire rule, it is at the same potential as the low potential side of the battery. Here and here, in A and C, X is also connected by nothing but wire to the other pole of the battery. Here's the one case that might superficially seem different. There's another circuit element in between point X and the high potential pole of the battery, but because there's no current, there's no potential difference between the two ends of that circuit element. All right, so now you've got some to try for yourself.